Cool. Hi. I think I've met a fair number of you. I'm Mike. I work at the University of Washington on EoR science. And today I want to discuss the SSINS of the MWA EoR Highband. This will be a slightly more traditional RFI approach, I think. Here's my talk outline. So first I'm going to review SSINS. I talked about it in Nagoya, but I'll go over it real quick again. So this is, again, it's an ultra-faint RFI flagging package developed on EoR data. Then I want to talk about the process of characterizing a data set using SSINS and characterizing its RFI content. And then I want to show some results of SSINS on the MWA EoR Highband, and then I'll present a summary. So let's start with the review. So it stands for Sky-Subtracted Incoherent Noise Spectra. There's a clue as to how it works. So it looks for ultra-faint RFI, which we classify as RFI that is fainter than the single baseline thermal noise, so just like really quiet stuff. And we have written a paper about it. It's on the archive at this link. There's a GitHub link to the software here, and there are documentations and tutorials for the software. I play tested these tutorials on 4 undergraduates. They made it through. They work. Okay. Okay, so let's talk about the algorithm a little bit, and this is all detailed in much more detail in the paper. So let's start with a single baseline. So this is the real component of the east-west polarization of some visibilities on a single baseline. We've got time on the vertical axis. I should probably use a pointer. Does this thing work? Okay. So yeah, time increases going down, frequency increases going to the right. The first step in SSINS, first order of business, is subtracting the sky out of the data. So what we do there is we perform a step that we call sky subtraction. So we take a time difference of neighboring visibilities and take their amplitude. So the reason for this is to, since the sky varies slowly over the course of an integration, this should subtract out the sky but leave thermal fluctuations and any RFI that also varies on that time scale. So this just kind of takes the sky out of the picture, which is nice. So this is, I've shown this process for a single baseline. We do this for every baseline, and then we get a big sensitivity boost. This is how we sneak under the single baseline thermal sensitivity. We average these amplitudes over the set of baselines. So this is what I call a sky-subtracted incoherent noise spectrum. And it's incoherent because we're just averaging the amplitudes. We're losing track of the phase in this subtraction. And so this is averaged over all the baselines. And it's probably kind of hard to see on this projector. I can barely make it out, but there's actually a smudge in the spectrum. It turns out that this smudge is RFI. So the way that we'll get around to understanding the smudge a little bit better is we'll use a process called mean subtraction to boost the contrast of the smudge with the rest of the data. So we're going to take a time average in each of these frequency channels and then normalize with respect to a standard deviation, and the result is this. This is the same data, but just with mean subtraction. And so you can see that that smudge I referred to is now this bright red rash. It happens to be about 7 megahertz wide, and there's another fainter rash right here. So if you go and check the spectrum allocation for digital television in Western Australia, you'll find that it starts at 174 megahertz and is about 7 megahertz wide. So this is a likely candidate for DTV RFI, and that's about the right size as well. So it turns out this indeed is DTV RFI. So a point that I want to make here is that after doing this mean subtraction, what we've actually done, since we've also normalized with respect to standard deviation, is we've actually written the data in terms of a z-score. So this tells you how far outlying each data point is from its time average in each frequency channel. Okay, and just as a side note, and this is in the paper, we can also find the z-score of a subband by summing over that subband. So we can actually find how far outlying this cluster of points is relative to what we expect for a clean observation. Okay, so how do we flag these shapes? So we use what we call a frequency match flagger or match filter or match shape filter. They're all names for the same thing in this book. So this is a programmable iterative filter that searches over user-defined subbands. So this is just a little flowchart for how it works. So you start with the SSINS, you do the mean subtraction and calculate your z-scores. And then if you have shapes that you're interested in, like DTV, you do a little subband sum and get those z-scores. Then you hold a little tournament and find who the strongest outlier is, whether it's a shape or just a single frequency channel. And then if the champion is greater than a significance threshold, you set at the front, then you flag it, and you repeat this process until there are no more that are past the threshold. And then the observation is deemed clean by the flagger. So here are results on the previous observation without programming in any subband. So this is just using the basic iteration here. And you can see that it grabs most of the DTV6 RFI, but this DTV channel 7 RFI is mostly untouched if you don't program in a subband. And that's because this is actually so faint that on a single sample basis, this RFI actually is not significantly far outlined. You actually have to program in the subband to see this ultra-faint RFI, or to flag this ultra-faint RFI in a statistically significant way. So when we program in the subband information, we see that it actually excises these features quite neatly. Okay, so that was a lot of information really fast. Here's a little video of the flagger going. So you can see it starts with the channel 6 stuff to begin with, and then in a second it'll hop over to the channel 7 stuff. And as it cleans up each of the channels, the rest of the data in that channel, which is of course changed, the mean estimation is changed when you flag more and more of the data. So at the end, this stuff that was biased blue earlier due to the biasing upward from the RFI actually starts to look more like the clean thermal noise that you expect at this stage. Okay. Cool. So how do we pick subbands? How do we know to use those shapes? So basically, we look at the data. So since each observation is compressed to a single waterfall per polarization, you can actually look at many hours of data in a short time frame. So this is actually a process that I went through. I made like 3,000 of these plots, literally, and just went through and cataloged various shapes that were in the data and reconciled them with the spectrum allocation. It just takes a few days of sweat and blood. And then you can program those into the match filter and then cross-match by eye, and we happened to find good agreement. There were no more other shapes that were revealed after we did our first go-around with the match filter. Well, there was actually one more. It's in the paper. I'll talk about it maybe a little bit in a bit. Okay, so we've done this for the EoR Highband. Ideally, this could be done... Ideally, this could be done for other observing bands, but I've got to graduate at some point, so hopefully the idea is that users of the MWA could pick up this software and learn these steps and use it to identify RFI in the observing bands that they know and love, and program their own match filters. Let's talk about some common SINs in the EoR Highband. So we have faint broadband streaks. You can barely see them here, but they show up here. We don't know what physically causes these because they're not band limited, but we can program that shape into the filter anyway. We also get narrowband RFI. There's a bit of a problem with this since it contaminates the entire observation. What tends to happen is the mean estimation is always corrupted, and so it tends to be incompletely flagged down in here. It's hard to see on the projector, but we have some workarounds for that. So basically, when a certain amount in a channel is flagged, we just flag that whole channel, and that's how we solve that problem, and we're working on upgrades to that detection algorithm. And then, of course, there's DTV, and there's actually a slightly more subtle shape that's a pre-processing artifact from Cotter that I won't talk about right now because I don't have time. I actually made images of this. I won't show those images right now, but we can talk about it later. I'll show you later if you want. It's actually posted with the paper on the archive. Right now I want to talk about our occupancy study. So this is the Julian date and days. Each of these dots is an observation. This just shows the fraction of samples that were flagged in the SINs. This is after AO flagger, so this is leftover RFI after AO flagger. And this is actually a data set that was used in the Beardsley et al. 2016 limit and is used in the Berry et al. 2019 limit that is in the review process right now. And you can see on each night there are some observations missing. So these were taken out in jackknife tests in the 2016 limit. So these are the remaining high-quality observations that still clearly have quite an occupancy. So black means no occupancy. You can see black ones are few and far between. So these are observations with TV occupancy, and you can see that about a third of these observations have DTV contamination, which is a lot more than I expected. When I first developed the filter, it was a lot more than I saw by eye, but if you go, you can see that there's actually these little faint DTVs that are hiding in there. So we expect RFI to badly affect the 21 centimeter power spectrum due to the fact that there's non-trivial frequency structure, so we wanted to know how bad it was. So this is a figure from this paper, and So the top is the east-west polarization, the bottom is the north-south polarization. These are 1D power spectra, and blue is after removing RFI, and green is before removing RFI. So what we did is we experimented with progressively severe DTV contamination. We found that the limit only got better, so we just took out everything that had DTV and any observation that had 40% total occupancy. So this is about a third of the data in total. And we found that the lowest bin dropped by a factor of 3.7. Smaller effects in these bins, and these noise-limited bins actually got worse. Okay, so takeaway is I think that SSINS really helped us out in our analysis, and we expect that it can help your analysis, and I would love if people got on board and used this software and found other things in the MWA. That would be really great, and there's links here for you to use. Okay, a little longer than I thought.
I didn't spook you so much, but Ramesh mentioned some of the stuff that Steve Prabhu was doing on the space situational awareness, looking at reflected RFI from satellites. In the paper that we just about, I think, has been submitted, he finds reflected RFI, but we also find CubeSats that are transmitting dramatically out of band to the level that they're sort of across just about the entire MWA frequency range.
I think at the tail of the...
It's something. They've got their allocated telemetry bands, but presumably cheap components and, amateur construction. We're not sure what the reason is, but it bleeds across the entire band. It's really useful to unleash some of your techniques on those sorts of things to see if this is a generic problem with CubeSats or just a couple that we found. And so, how does all this deal with something that's moving across the sky?
Here, let's watch a video. So I showed a DTV event earlier. Part of the observation was contaminated. The rest of it was not. What we did was we calibrated on the clean part of the observation, transfer that calibration to the contaminated part, and then image the contaminated part in snapshots, 2-second snapshots. And I'll show it frame by frame here. So you can see there's some sort of unidentified flying object moving down here.
And it shows up very brightly in his figure there.
Yeah, it's got like 80 sigma in single samples alone. If you average over the subband, it's like some hundreds of sigma. So I think it catches moving stuff, and we also have other examples like here. This Miguel showed this earlier. This is a similar situation where I imaged some DTV, and you can see this streak down here. But this is kind of a projection effect. This streak is much longer than it looks here, so we can infer some motion from the streak. And we've seen a few cases like this at about, I think it's like 9:30 or 10:30 at night.
So we're ages staring at these particular few observations. I wonder if it would be interesting to point you to the opt IDs and just see what you make of them.
Yeah, I can see if there's SSINS in there. Probably will be. Most data is sinful. Yeah, I don't know. I could take a look. Ideally, I could get someone else to take a look too. That would be brave enough.
We've got tutorials.
I do have tutorials.
Alright. Anybody else have a question? I feel like I'd be remiss if I didn't ask what happens when we train neural nets to make new mass filters.
That is a fascinating question, and I don't know the answer to it because I don't know a thing about neural nets. So.
I think it's important to think that the SSINS and your way of flagging based on what you see in SSINS don't have to go hand in hand.
Yeah.
You can make the test back into the noise spectrum across lots of ways to flag them.
That's right.
Alright, very close together.
During the last 15 years, rise, I guess, of Bayesian type analyses, there's been a lot of negativity towards the so-called sigma clipping, which is basically iteratively throwing out data that are outliers.
Yeah.
Is that not exactly what you're doing?
That is exactly what I'm doing.
So the reason that's been declared sinful is that it's difficult to reproduce without, it's because it's very algorithmical, you're making a choice, and it's like a series of
It's a
branches.
bit chaotic.
It's this loop, it's just like clean in an image sense or something like that. Have you found that this is simple enough that it's reproducible in that way, or are you a little concerned about that in the long run, as people start adding more complicated rules, going down the road? Not necessarily your
I think it's pretty simple. I think it's a pretty simple algorithm right now, and as far as shapes that I see in the spectrum by eye, I think it catches those shapes fine. Sometimes it thinks there's DTV somewhere that my eye can't pick it out, but the map says it's there. So maybe it's a bit aggressive, but I don't.
Nothing you define separate spectral stuff.
But the other thing is that the way that it's perceived, actually the same metric, right? So it's not as finely tuned to different pictures. All are very simple use for metrics. I mean, it is iterative.
That's why I was.
But I think it's a little bit more simple than some of the ones that you're talking about.
Kind of define it, so you can apply the based on it.
That's possible.
They don't have.
Yeah,
Let's let Mike relax.